Hey there, welcome back to the channel, and today we're about to embark on what might be the most mind-bending journey we've ever taken together. I want you to do something for me right now. Just pause and look around you. Look at your hands, your phone, the walls, the sky outside your window. Everything feels so real, doesn't it? So solid, so permanent, well, there. But what if I told you that everything you're seeing, everything you remember, every single moment of your life up until this very second, might be nothing more than a fleeting hallucination, a cosmic glitch in the fabric of nothingness, that you might not be a real person sitting in a real room watching a real video, but instead, a disembodied brain that spontaneously popped into existence just a moment ago, complete with fake memories of a life that never happened. I know, it sounds absolutely insane, like something straight out of a science fiction movie that even Christopher Nolan would find too weird. But this is a genuine scientific paradox that has been keeping the smartest physicists on our planet awake at night for over a century. It's called the Boltzmann Brain Paradox, and by the end of this video, you're going to be questioning everything you thought you knew about reality itself. So if you're ready to have your mind blown into a million tiny pieces and then have those pieces questioned for their own existence, do me a favor. Hit that like button right now. Subscribe if you haven't already. And when you're done watching this, I want you to comment down below with your location and what time it is where you are, because I am genuinely curious to know where and when in this supposedly real universe you're watching this from. And with that said, let's dive into the rabbit hole. Now, before we can even begin to understand what a Boltzmann brain is, we need to start with something that seems deceptively simple, something you experience every single day without even thinking about it. I want you to imagine you're making yourself a cup of coffee in the morning. You take your mug, you pour in the hot coffee, you add some milk, and then you give it a good stir with a spoon. The milk swirls around and eventually mixes perfectly with the coffee, creating that beautiful brown color we all know and love. But here's the thing. Once you've stirred that milk in, it never unstirs itself, does it? You never see the milk suddenly separate from the coffee and climb back up your spoon. Or think about an ice cube sitting on your kitchen counter. It melts into a little puddle of water, but that puddle never spontaneously reforms itself into a perfect ice cube. Or imagine dropping a glass on the floor. It shatters into hundreds of pieces, but those pieces never leap up from the floor and assemble themselves back into a perfect, unbroken glass. This, my friends, is the one-way arrow of time, and it's governed by one of the most fundamental laws of the universe, a law so important that it's practically the boss of everything that happens in our daily lives. It's called the second law of thermodynamics, and it basically says that everything in the universe tends to move from order to disorder, from neat and tidy to messy and chaotic, and it never goes the other way around unless you put energy into the system. But let's break this down even more, because the word disorder can be a bit confusing. Scientists actually have a special name for this disorder. They call it entropy. Think of entropy as the universe's way of measuring how messy things are. A brand new deck of cards, perfectly arranged from ace to king in each suit, has very low entropy because it's highly ordered. But when you shuffle that deck thoroughly, the entropy goes way up because now the cards are in a random, chaotic order. And here's the kicker. There are only a very few ways for that deck to be perfectly ordered, but there are billions upon billions of ways for it to be shuffled into randomness. So, entropy isn't just about messiness. It's about probability. The universe, it seems, is playing a giant game of chance, and it's always betting on the outcome that has the most possible combinations, which just so happens to be the messy, chaotic, random ones. Now, this concept was pioneered by an absolutely brilliant Austrian physicist named Ludwig Boltzmann, who lived in the late 1800s. This guy was a genius, but his life was actually pretty tragic, which makes his story even more compelling. Boltzmann was one of the first scientists to really understand that all the laws of thermodynamics, things like heat, energy, and temperature, weren't just abstract concepts, but were actually the result of countless tiny particles like atoms and molecules bouncing around and colliding with each other. He realized that when you feel the warmth from your coffee cup, what you're actually feeling is the result of millions of microscopic particles moving faster and hitting your skin. But here's where it gets really interesting. Boltzmann applied this statistical way of thinking to entropy, and what he discovered was both fascinating and deeply unsettling. He figured out that while the universe overwhelmingly prefers to move toward disorder, toward high entropy, there's always a tiny, unbelievably tiny chance that things could spontaneously move in the opposite direction. It's like if you shuffled that deck of cards a trillion times, you might, by pure random chance, accidentally shuffle it back into perfect order. The probability is incredibly small, but it's not zero. And this is where our story takes a turn from everyday kitchen observations to the vast, mind-bending scale of the entire cosmos. You see, Boltzmann wasn't just thinking about coffee and ice cubes. He was thinking about the entire universe, about space and time and everything that has ever existed or will ever exist. He proposed that if the universe was infinitely old or infinitely large, then even the most improbable events would not just become possible, they would become inevitable. Given enough time, even something as absurdly unlikely as all the air molecules in your room suddenly gathering in one corner, leaving you gasping for breath in a vacuum, would eventually happen. It might take longer than the age of the universe countless times over, but in an infinite timeline it would happen. And then it would happen again. And again. In fact, it would happen an infinite number of times. Now at this point, you might be thinking, okay, that's weird and all, but what does this have to do with brains floating in space? And I'm getting there, I promise, but you need to understand this next part because it's absolutely crucial to the paradox. Boltzmann took this idea and applied it to the biggest question of all. Why does our universe exist? Why is there something rather than nothing? And more specifically, why is our universe so incredibly ordered and structured? We have galaxies, stars, planets, complex life, human beings with brains that can think and create and watch YouTube videos about their own existence. This is a state of very low entropy, very high order, and according to the second law, it shouldn't really be here. It should have decayed into chaos long ago. So Boltzmann proposed that maybe our entire universe is just a statistical fluctuation. Maybe in an infinitely old, infinitely large, high-entropy universe, there was a random, rare, but inevitable fluctuation where particles just happened to come together in exactly the right way to form our universe as we know it. Maybe the Big Bang itself was just a particularly large hiccup in the eternal void of chaos. But here's where things get really, really weird. In 2002, two physicists named Andreas Albrecht and Lorenzo Sorbo took Boltzmann's idea and pushed it to its absolute logical extreme. And in doing so, they created one of the most existentially terrifying concepts in all of modern physics. They asked a deceptively simple question. If our universe really is just a random fluctuation from chaos, what's the smallest, simplest, most probable fluctuation that could create an observer? And the answer they came up with is absolutely chilling. You see, creating an entire universe with billions of galaxies, trillions of stars, and 14 billion years of history is an enormously complex, enormously improbable fluctuation. It would require countless particles to come together in precisely the right way. But creating a single brain, that's much simpler. Creating a brain that has all the memories and thoughts and perceptions of a human being who believes they're living in a vast universe. That's still incredibly complex, but it's far, far less complex than creating an actual universe for that brain to live in. In fact, the difference in probability is so vast that it's like comparing winning the lottery once versus winning the lottery every single day for a trillion years. So the Boltzmann Brain Paradox goes like this. In an infinitely old, high-entropy universe, it is far, far more likely that you are a disembodied brain that spontaneously formed a moment ago, complete with fake memories of your entire life, than it is that you are a real human being who evolved over billions of years in a real universe that formed from a real Big Bang. Think about that for a second. Every memory you have of your childhood, your first kiss, your favorite movie, the first time you watched a video on this channel. All of it could be completely fabricated, implanted in a brain that formed from random particles in the void. You might not be sitting in a real room. You might not even have a body. You could be a brain floating in empty space, a fleeting fluctuation that will disappear back into nothingness in the next instant, and you would never even know it. All of your senses, sight, sound, touch, taste, could be complete illusions, just electrical signals in this randomly formed brain that make you think you're experiencing a real world. Now, I know this sounds completely bonkers, like the kind of thing you'd come up with at 3 in the morning after too much caffeine, but this is a serious scientific argument that has real mathematical backing. To understand why, we need to dive a little deeper into probability and the concept of infinity. But I promise I'll keep it as simple as possible because this is genuinely important. Imagine you have a box filled with gas particles like air molecules, and these particles are just bouncing around randomly. Most of the time, they're spread out evenly throughout the box, which is the high entropy, high probability state. But occasionally, by pure chance, they might all cluster in one corner. Rarely, they might even form a simple shape. Given infinite time, they would eventually form every possible arrangement, including exact replicas of complex objects. And this is the key point, they would form simple objects far more often than complex ones. A single brain is astronomically simpler than an entire universe containing that brain. It's like the difference between randomly typing letters on a keyboard and accidentally typing the word hello versus accidentally typing the entire works of Shakespeare. Sure, both are possible given infinite time, but one is going to happen unimaginably more often than the other. Let's talk about just how big these numbers are, because your brain literally cannot comprehend them, and that's not an insult. No human brain can. The estimated timescale for a Boltzmann brain to form through quantum fluctuations in a vacuum is about 10 to the power of 10 to the power of 50 years. That's a number so large that if you wrote a 0 on every single atom in the entire observable universe, you still wouldn't have enough atoms to write it out. Our universe is only about 14 billion years old, which is basically a blink of an eye compared to that timescale. So, if the universe really does last forever, then over infinite time, these Boltzmann brains would form an infinite number of times. In fact, they would form so much more frequently than entire universes that the probability ratio is something like a googolplex to 1. That means for every one real universe with real observers, there would be a googolplex of these fake brains with fake memories. But wait, it gets even weirder. Some physicists have pointed out that Boltzmann brains wouldn't necessarily just blink into existence fully formed. They might form gradually through a series of smaller fluctuations that happen in reverse order from how a brain would normally decay. So, you might start with a few particles that come together, then a few more, gradually building up into a brain over what seems to us like an instant, but in reverse. This brain would have exactly one coherent thought, maybe something like, I exist, or I am thinking this thought, and then it would immediately start decaying back into chaos. The entire lifespan of a Boltzmann brain might be less than a nanosecond, but because its memories are fake, it would perceive itself as having lived an entire lifetime. That thought you're having right now, reading this sentence, might be the only thought a Boltzmann brain ever has, and the entire memory of how you got to this moment could be a fabrication. Now at this point you might be thinking, okay, this is interesting and all, but how do we know this is just a thought experiment and not something that's actually happening to me right now? And that's a great question, because it's exactly what scientists have been grappling with. You see, when Albrecht and Sorbo proposed the Boltzmann brain concept, they didn't actually believe we were Boltzmann brains. They used it as what's called a reductio ad absurdum argument, which is a fancy Latin way of saying, if your theory leads to an absurd conclusion, then your theory is probably wrong. The absurd conclusion here is that you, the person watching this video, are more likely to be a fake brain than a real person. Since that seems obviously ridiculous, since you're clearly real, right? Then there must be something wrong with the assumptions that led us to this paradox. So what are those assumptions? Well, the main one is that the universe is infinite in both time and space, and that it can exist in a high entropy state for an infinite amount of time. Our current best theories of cosmology actually suggest something different. We now know that our universe is expanding at an accelerating rate, and if this continues, eventually all the stars will burn out, all the black holes will evaporate, and the universe will become a cold, dark, empty place with nothing but radiation getting thinner and thinner. This is called the heat death of the universe, and it represents a maximum entropy state. But here's the thing. If the universe keeps expanding forever, it might never actually reach a true equilibrium where Boltzmann fluctuations can happen. The expansion itself might prevent these random fluctuations from ever having enough time or energy to create something as complex as a brain. So one way out of the paradox is that our universe has a finite lifespan, or at least a finite period where it can support observers, which would make the formation of Boltzmann brains incredibly unlikely rather than inevitable. But there are other ways out too. Some physicists have proposed that our understanding of probability breaks down when dealing with infinite universes. Others have suggested that maybe the laws of physics themselves prevent such fluctuations from creating self-aware observers. And still others have argued that the very concept of counting probabilities across infinite time doesn't make sense. You can't really say something is more likely to happen in infinity because everything that can happen will happen an infinite number of times, which makes comparing frequencies kind of meaningless. This gets into some really deep philosophical territory about what probability even means in the context of infinite universes, which is a whole other rabbit hole we could go down. But I want to stay focused on the core paradox because it's already mind-bending enough as it is. Now let's talk about why this paradox is so personally unsettling, because that's what makes it more than just an abstract physics problem. The Boltzmann Brain Paradox strikes at the very heart of what it means to be you. Your sense of self, your memories, your subjective experience of consciousness, all of these could be illusions if you're a Boltzmann brain. And the really creepy part is that there's no way for you to prove you aren't one. Any evidence you could gather, any test you could perform, any logical argument you could make could itself be part of the fake memories. You could look at your hands and say, "See, I have a body, I'm real." But a Boltzmann brain would have memories of looking at its hands too. You could look at the consistent laws of physics and say, "See, the universe is orderly." But a Boltzmann brain would have memories of observing those same laws. You could even do scientific experiments and verify them with other people, but those other people and those experimental results could all be part of the hallucination. This leads to what's called a skeptical hypothesis. You can't disprove it, which makes it philosophically troubling, even if it's physically unlikely. This isn't actually the first time we've encountered this kind of existential doubt in philosophy. Back in the 1600s, a French philosopher named René Descartes asked a similar question. How do you know that an evil demon isn't feeding you false sensory information, making you believe in a world that doesn't exist? In modern times, this has been updated to the brain in a vat scenario. How do you know you're not just a brain in a laboratory somewhere, hooked up to a computer simulation that creates all your experiences? The Boltzmann Brain Paradox is like the universe's version of this, except it doesn't require an evil demon or a mad scientist. It just requires infinite time and random chance. It's a naturally occurring brain in a vat, where the vat is the void of empty space and the brain is a statistical accident. But here's where I want to offer you some comfort, because as fascinating as this paradox is, I don't want you to go to bed tonight genuinely believing you might be a fake brain. There are some very good reasons to think that we're real, that this universe is real, and that your experiences are genuine. First, there's the principle of parsimony, also known as Occam's razor, which basically says that the simplest explanation that fits the evidence is usually the right one. The idea that you're a Boltzmann brain requires an infinite universe, infinite time, and a specific type of random fluctuation. The idea that you're a real person in a real universe requires only that our current understanding of cosmology and evolution is correct. That's a much simpler explanation. Second, there's the fact that our observations of the universe are incredibly consistent. The laws of physics work the same way everywhere we look. The cosmic microwave background radiation, which is the afterglow of the Big Bang, matches our predictions perfectly. The distribution of galaxies, the expansion of space, the behavior of subatomic particles, all of it fits together in a way that would be incredibly unlikely to occur by random chance in a Boltzmann brain scenario. A randomly formed brain might have memories of consistency, but it would be extraordinarily improbable for those memories to match the actual deep structure of physical law that we observe when we do careful experiments. There's also the fact that we share this reality with other observers. I know I just said that other people could be part of the hallucination, but think about it. The fact that we can have this conversation, that you can comment below and other people can read your comment and respond, that we can build on each other's knowledge and verify each other's observations, strongly suggests that we're all part of the same objective reality. If you were a Boltzmann brain, your memories of other people would be fake, but you wouldn't actually be able to interact with them in a way that surprises you or teaches you something new. The fact that we can learn from each other, that we can be surprised by what someone else says, that we can test our hypotheses against independent observations, all of this points to a shared reality rather than a solipsistic one where only you exist. And here's another thing to consider. The Boltzmann brain paradox depends on some assumptions about probability and infinity that might not actually be correct. When we talk about an infinite universe, we don't really know what that means. Infinity is a mathematical concept, but is it a physical reality? Our universe might be finite. It might have a beginning and an end. It might have a finite amount of matter and energy. And if that's the case, then Boltzmann brains might be impossible, or at least so incredibly rare that we don't have to worry about them. Additionally, our understanding of quantum mechanics at the cosmological scale is still incomplete. We don't have a theory of quantum gravity that works for the entire universe, and it's possible that such a theory would rule out these kinds of fluctuations entirely. The vacuum of space might not be able to produce complex structures through quantum fluctuations in the way we've been assuming. But let's set aside the question of whether we're actually Boltzmann brains for a moment, because even if we're not, the paradox still has profound implications for how we think about the universe and our place in it. It forces us to confront the fact that our existence is, in some sense, incredibly unlikely. The fact that we have this ordered, complex, life-supporting universe is not something to be taken for granted. It's what physicists call a fine-tuning problem. The laws of physics and the initial conditions of our universe seem to be set up in just the right way to allow for stars, planets, and life to exist. If any of the fundamental constants, things like the strength of gravity, or the mass of an electron, or the speed of light, were even slightly different, our universe would be a lifeless void. So why is our universe so perfectly set up for us? This is where the Boltzmann brain idea connects to other big cosmological theories. Some scientists have proposed that our universe is just one of many in a vast multiverse. In this multiverse, each universe might have different physical constants, different laws of physics, different initial conditions. Most of them would be dead, lifeless, high-entropy voids, but a few, by sheer chance, would have the right conditions for life. And of course, we only find ourselves in one of those life-friendly universes because we wouldn't be around to observe the dead ones. This is called the anthropic principle, and it provides a neat solution to the fine-tuning problem. But the Boltzmann brain paradox points out that even within this multiverse scenario, it's more likely for a Boltzmann brain to form in a dead universe than for a whole life-friendly universe to exist. So if the multiverse is real and infinite, we're back to the same problem. We're more likely to be Boltzmann brains than real observers. This has led some physicists to propose that there must be something fundamentally wrong with the idea of an infinite multiverse. Maybe the multiverse doesn't exist. Maybe it's finite. Or maybe there's some physical principle we haven't discovered yet that makes the formation of Boltzmann brains impossible, even in infinite space and time. For example, maybe consciousness requires more than just a randomly assembled brain. Maybe it requires a brain that has evolved and developed over time, interacting with a real environment. Maybe a brain that just pops into existence can't actually be conscious, even if it has the right structure. We don't really understand consciousness well enough to say for sure, but it's a possibility. There's also the question of what we mean by probability in this context. When we say it's more likely that you're a Boltzmann brain, we're using a certain notion of probability that works well for flipping coins or rolling dice, but might not apply to questions about the existence of entire universes. Some philosophers and physicists argue that we should use a different kind of reasoning when thinking about cosmological questions, a reasoning based not on counting possible outcomes, but on explaining the observations we actually have. This is called the principle of typicality, and it says that we should assume we're typical observers in the universe, not rare statistical flukes. If we accept this principle, then the fact that we observe a vast, ordered universe suggests that we are real observers in a real universe, not Boltzmann brains. But here's where it gets really interesting, and maybe a little bit hopeful. The Boltzmann Brain Paradox, despite its existential terror, is actually a testament to the power of human reasoning. Think about it. We've figured out how to use the laws of physics and statistics to think about scenarios that might be beyond our ability to ever directly observe. We've used mathematics and logic to peer into the far, far future of the universe and ask questions about the nature of reality itself. Even if the paradox is ultimately resolved and we conclude that we're not Boltzmann brains, the fact that we can even conceive of such an idea and reason through its implications is absolutely remarkable. It shows that our brains, whether they're Boltzmann brains or not, are capable of grasping abstract concepts and following logical arguments to their conclusions, even when those conclusions are deeply unsettling. And that brings me to another point. The Boltzmann Brain Paradox is a great example of how science and philosophy are deeply intertwined. This isn't just a physics problem. It's a problem about knowledge, about what we can know, about what it means to be an observer, about the nature of reality itself. These are questions that philosophers have been asking for thousands of years, and now physicists are joining the conversation using the language of mathematics and observation. This cross-pollination of ideas is one of the most exciting things about modern science. It shows that the big questions, who are we? Why are we here? Is any of this real? Aren't just the domain of mystics and poets. They're questions that we can approach scientifically, using evidence and reason, even if we can't always get definitive answers. Now, I want to take a step back and talk about the person who started all this, Ludwig Boltzmann. Because understanding his story helps us understand why he was thinking about these kinds of problems in the first place. Boltzmann lived in a time when the existence of atoms wasn't universally accepted. Many scientists, including some very famous ones like Ernst Mach, thought that atoms were just a convenient mathematical fiction, not real physical objects. Boltzmann was one of the few who insisted that atoms were real, and he developed his statistical mechanics as a way to prove it. He showed that if atoms were real, then you could explain things like temperature and entropy in terms of their motion. But his ideas were controversial, and he faced a lot of opposition from the scientific establishment. Some historians think that this opposition contributed to his depression. In 1906, while on vacation with his family, Boltzmann hanged himself. He was 62 years old. It's a heartbreaking story, and it adds a layer of poignancy to his work. This man, who gave us the tools to understand the statistical nature of reality, was himself consumed by the weight of his own thoughts. But his legacy lived on. Decades after his death, experiments confirmed the existence of atoms beyond any doubt. His statistical mechanics became one of the cornerstones of modern physics. And today, we use his ideas to understand everything from how engines work to how stars shine to why ice melts. And yes, we also use them to think about Boltzmann brains. I sometimes wonder what Boltzmann would think if he could know that his work led to such bizarre and unsettling conclusions. Would he be horrified, amused, proud? I like to think he'd be fascinated because he was clearly someone who loved to follow an idea wherever it led, even if it led to controversial places. Let's talk about some of the ways that scientists have tried to resolve the Boltzmann Brain Paradox, because this is where the story gets really interesting from a physics perspective. One of the most popular solutions is based on something called inflationary cosmology. According to this theory, in the very early universe, space underwent a period of incredibly rapid expansion. This inflationary period would have smoothed out any random fluctuations and set the initial conditions of our universe to be very low entropy. But more importantly, inflation suggests that our universe might be much larger than what we can observe, maybe infinitely large. And in an infinitely large universe, you can have an infinite number of regions that are like our observable universe, each with slightly different conditions. This is a different kind of multiverse than the one we talked about earlier. In this scenario, most of the universe is in a high-entropy state, but there are infinite patches of low-entropy regions where life can exist. The key insight is that, in this kind of multiverse, real observers like us would actually be more common than Boltzmann brains, because the low-entropy patches provide the right conditions for actual evolution and galaxy formation. The Boltzmann brains would still exist, but they'd be swamped by the much larger number of real observers. This solves the paradox by making us typical rather than exceptional. Another possible solution comes from quantum mechanics itself. Some interpretations of quantum theory suggest that the universe doesn't have a single history, but rather a quantum superposition of many possible histories. In this view, the probability of a Boltzmann brain forming isn't just about random fluctuations in a classical sense, but about the quantum wave function of the universe. And some physicists have argued that the quantum state of our universe is such that the probability of Boltzmann brains is essentially zero. This is still a very speculative area of research, but it shows that our incomplete understanding of quantum gravity might hold the key to resolving the paradox. There are also more exotic solutions. Some theories suggest that the universe might end in a big crunch, where expansion reverses and everything collapses back together. If that happens, then the universe would have a finite lifespan, which would prevent Boltzmann brains from forming. Or maybe the universe goes through infinite cycles of big bangs and big crunches, but each cycle is finite, which again would prevent the formation of Boltzmann brains. Or maybe there's a fundamental physical principle that we haven't discovered, yet that makes the formation of conscious observers require a real evolutionary history, not just a random assemblage of neurons. We simply don't know enough about consciousness to rule this out. I want to take a moment to address something that might be bothering you. If you're anything like me, when you first hear about the Boltzmann brain paradox, you might feel a sense of existential dread, a kind of vertigo where the ground of reality seems to fall away beneath your feet. You might find yourself looking in the mirror and wondering, am I real? Are you real? Is any of this real? And that's a completely normal reaction. The paradox is designed to unsettle us, to challenge our most basic assumptions about existence. But I want to offer you a different perspective. Instead of seeing this as a reason to doubt your own reality, try seeing it as a reminder of how precious and unlikely your existence actually is. Whether you're a Boltzmann brain or not, and I personally believe we're not, the fact that you can ask these questions, the fact that you can contemplate your own existence, the fact that you can experience wonder and curiosity and awe is absolutely miraculous. The universe, whether it's real or simulated or fluctuated into existence, has somehow produced the conditions for consciousness, for self-awareness, for meaning. And that, to me, is more profound than any paradox. Think about it this way. Every single one of us is standing on a knife edge of probability. The universe could have been lifeless. The Earth could have never formed. The first self-replicating molecule could have never emerged from the primordial soup. Your parents could have never met. The sperm that became you could have been a different one. The chain of events that led to you being here, right now, watching this video, is so astronomically improbable that it's practically a miracle. And yet, here you are. The Boltzmann Brain Paradox is just the cosmic, ultimate version of this improbability. It's asking us to consider not just the improbability of your existence, but the improbability of existence itself. And the answer, whether it's we're real or we're a fluctuation, is still mind-blowing. Let me try to explain the paradox in yet another way, because I really want you to grasp just how deep this goes. Imagine you're playing a game of Minecraft, and you've built this elaborate world with castles and farms and redstone contraptions. You've spent hundreds of hours on it. Now imagine someone tells you that your entire Minecraft world is just a randomly generated seed. No player, no design, just pure random chance that happened to produce something that looks intentional. That's kind of what the Boltzmann Brain Paradox is suggesting about our universe. It's saying that all this complexity, all this order, all this beauty, might just be the result of cosmic dice rolling for long enough. But then it goes one step further and says, actually, it's even more likely that just your character in Minecraft exists, with fake memories of building all those things, and the world itself doesn't exist at all. That's the level of existential weirdness we're dealing with here. Your character, with its inventory and its memories and its achievements, is simpler to generate than the entire world it remembers building. And here's another angle that might help you understand why this is such a big deal in physics. For a long time, scientists have been trying to figure out the initial conditions of our universe. Why did the Big Bang produce a universe with such low entropy? Why is it so perfectly set up for life? This is called the past hypothesis, the idea that the universe started in a very special, very low entropy state. The Boltzmann Brain Paradox is essentially saying that if you try to avoid the past hypothesis by saying the universe is just a random fluctuation, you end up with a scenario where most observers are Boltzmann brains. So you can't have it both ways. Either the universe had a special low entropy beginning, which raises questions about why it started that way, or you have to accept that you're probably a Boltzmann brain, which seems absurd. This is why the paradox is so powerful. It forces us to confront the fundamental mystery of why our universe is the way it is. Let's talk about some of the mathematical details, but I'll keep them very simple. The probability of a fluctuation creating a certain configuration of matter is related to its entropy. The lower the entropy, the less probable the fluctuation. Now, the entropy of our entire observable universe is estimated to be around 10 to power 104. That's a huge number, but the entropy of a human brain is much smaller, around 10 to power 25. The difference is staggering. This means that a fluctuation creating a brain is exponentially more probable than a fluctuation creating an entire universe. In fact, if you do the math, the ratio of probabilities is something like 10 to power 100 to 1. That's not just a big number. It's a number so big that it defies comprehension. To put it in perspective, there are about 10 to power 80 atoms in the observable universe. The number 10 to power 100 has more digits than there are atoms in the universe, and then you have to raise 10 to that power. It's literally unimaginable. And yet, that's how much more likely it is for you to be a Boltzmann brain than a real observer in a real universe, if the assumptions hold. Now, some critics have pointed out that this calculation might be too simplistic. It assumes that the probability of a fluctuation depends only on entropy, but maybe consciousness requires more than just a low entropy state. Maybe it requires a history, a process, a development over time. Maybe a brain that just pops into existence can't actually be conscious. even if it has the right structure. This is connected to the hard problem of consciousness, the question of why and how subjective experience arises from physical processes. We don't know enough about consciousness to say for sure, but it's possible that the statistical argument underestimates the complexity required for actual awareness. There's also the issue of time. A Boltzmann brain that forms and decays in a fraction of a second wouldn't have time to have a coherent train of thought. The electrical signals in the brain wouldn't have time to propagate. So maybe these fleeting fluctuations can't actually produce the kind of sustained experience that we have. But then again, if the memories are fake, the brain wouldn't need real time to have them. It would just have the memory of having had them. This is a bit of a philosophical quagmire, and it's one of the reasons why the paradox is so difficult to resolve. Let's also consider the quantum side of things, because this is where modern physics really comes into play. According to quantum field theory, even empty space isn't truly empty. It's filled with virtual particles that pop in and out of existence. This is called the quantum vacuum, and it's a seething foam of activity at the smallest scales. Now, if you wait long enough, it's theoretically possible for larger objects to appear through quantum fluctuations. A single particle might appear, then disappear. A pair of particles might appear. Given enough time, a whole atom might appear. But a brain, the probability is astronomically small. However, as we said before, in infinite time, even astronomically small probabilities become certainties. The calculation that a Boltzmann brain would appear after 10 to power 10 to power 50 years is based on quantum fluctuations in a vacuum. But if space is expanding, if the quantum vacuum itself is changing, then this calculation might be wrong. The energy density of the vacuum might be too low to support such a massive fluctuation, or the expansion might pull the brain apart faster than it can form. This connects to something called the measure problem in cosmology. When you're dealing with infinite universes or infinite time, it's not clear how you should count probabilities. What reference class should you use? Should you count observers per unit volume, per unit time, per unit of some other measure? Different choices lead to different conclusions, and there's no consensus on which choice is correct. Some physicists argue that the measure problem is the key to resolving the Boltzmann brain paradox, that once we figure out the correct way to calculate probabilities in an infinite universe, we'll find that the probability of being a Boltzmann brain is actually zero or negligible. But others worry that the measure problem might be unsolvable, which would leave us stuck with the paradox. Now, I want to bring this back down to earth for a moment, because I don't want you to think that this is just abstract theory with no connection to reality. The truth is, the Boltzmann brain paradox is part of a larger conversation in physics about the nature of time, the origin of the universe, and the future of everything. It's connected to questions about the arrow of time. Why do we remember the past but not the future? It's connected to the question of whether the universe had a beginning or whether it's eternal. It's connected to the question of whether the laws of physics are truly fundamental or just emergent properties of something deeper. These are the biggest questions we can ask, and the Boltzmann brain paradox is one of the tools we use to test our theories about them. For example, if a theory of cosmology predicts that Boltzmann brains should vastly outnumber real observers, that's a major problem for that theory. It suggests that the theory is incomplete or wrong. This is actually used as a criterion for evaluating theories of the multiverse. If your multiverse theory leads to a Boltzmann brain catastrophe, then your theory is probably not correct. This is called the Boltzmann brain problem in cosmology, and it's a serious challenge for many modern theories. So this isn't just a philosophical parlor trick. It's a constraint on our physical theories. It's a way of distinguishing between theories that make sense and theories that lead to absurd conclusions. Let's also talk about the psychological aspect of this, because I think it's important to acknowledge how these kinds of ideas affect us. When we confront the possibility that we might not be real, it can trigger a kind of existential anxiety. This is sometimes called cosmic vertigo, the feeling of being small and insignificant in the face of the vastness of the universe. But I want to suggest that there's another way to respond to this. Instead of feeling anxious, we can feel amazed. We can feel grateful. We can feel wonder at the fact that the universe has produced beings who can ask these questions at all. Whether we're Boltzmann brains or not, we're still part of something extraordinary. We're still the universe, or whatever is generating these experiences, becoming aware of itself. And that's a kind of magic that transcends the question of whether it's real or not. I also want to address a common misconception about the Boltzmann Brain Paradox. Some people hear about it and think, oh, so scientists think we might not be real. But that's not what scientists think. The overwhelming consensus is that we're real observers in a real universe. The paradox is a tool for testing theories, not a serious suggestion about our actual nature. It's like a reductio ad absurdum, as I mentioned earlier. If your theory leads to the conclusion that we're probably Boltzmann brains, then your theory needs to be revised. So when you read articles or watch videos about Boltzmann brains, it's important to understand that this is a problem that physicists are trying to solve, not a conclusion they've reached. That being said, the fact that the paradox exists at all tells us something profound about the limits of our knowledge. It tells us that there are questions we can ask that we don't yet have the tools to answer definitively. It tells us that our understanding of probability, of infinity, of consciousness, of the very nature of reality is still incomplete. And that's exciting. It means there's still so much to discover. It means that the universe still has secrets to reveal. It means that science isn't finished, that we're still on a journey of discovery, and that some of the biggest mysteries are still out there waiting for us. Now, I want to explore some of the more speculative and fun ideas that have come out of discussions about Boltzmann brains, because not everything about this has to be doom and gloom. Some creative thinkers have suggested that if Boltzmann brains can form, maybe they can form with all sorts of different structures and experiences. Maybe there are Boltzmann brains out there that are experiencing completely alien realities, with different laws of physics, different senses, different forms of consciousness. Maybe there are Boltzmann brains that are experiencing a single, perfect moment of bliss. Maybe there are Boltzmann brains that are experiencing what they think is a lifetime of adventure in a fantasy world. The possibilities are literally endless, because given infinite time, every possible configuration of matter that can exist will exist. This is sometimes called the infinite monkey, infinite time. A monkey randomly typing on a typewriter will eventually produce all the works of Shakespeare. Similarly, given infinite time, the universe will eventually produce every possible brain state, which means every possible experience that can be had will be had, even if only for a fleeting instant. Some people have even suggested that this might be a kind of cosmic immortality. If the universe lasts forever, then eventually, through random fluctuations, a brain exactly like yours will form again. It will have all your memories, all your personality, all your sense of self. It will think it's you. And in a very real sense, it will be you, because there's no way to distinguish between the original and the copy. This leads to all sorts of wild speculations about personal identity and what it means to be you. If a perfect copy of you forms in the far future, is it you? Or is it just someone who thinks they're you? These are questions that philosophers have been debating for centuries, and the Boltzmann brain scenario gives them a new, cosmic context. Let's also consider the computational aspect of this. Some physicists have pointed out that a brain is essentially a kind of computer, processing information and generating experiences. If we accept that, then the Boltzmann brain paradox becomes a statement about the probability of computational states. And this connects to other ideas in physics and computer science, like the simulation hypothesis, the idea that we might be living in a computer simulation. The Boltzmann brain scenario is like the natural, statistical version of the simulation hypothesis. Instead of being simulated by advanced beings, we're simulated by random chance. Both scenarios raise similar questions about the nature of reality and our ability to know it. I also want to touch on the emotional experience of contemplating these ideas. When I first learned about Boltzmann brains, I felt this strange mixture of terror and exhilaration. On one hand, the idea that I might not be real was deeply unsettling. But on the other hand, the sheer audacity of the concept, the way it expands the boundaries of what's possible, was incredibly exciting. It's like looking into the abyss and seeing not just darkness, but infinite possibility. And I think that's a healthy response. We should be able to hold these big, scary ideas in our minds without letting them crush us. We should be able to use them as tools for thinking, as invitations to wonder, rather than as sources of anxiety. In fact, I think the Boltzmann Brain Paradox can actually make us more appreciative of our lives, whether they're real or not. If we're real, then we're incredibly lucky to be part of this ordered, beautiful, meaningful universe. If we're Boltzmann brains, then we're incredibly lucky to have this moment of consciousness, this fleeting glimpse of something, even if it's an illusion. Either way, the fact that we can experience anything at all is a gift. The fact that we can love and learn and create and ask questions is something to be grateful for. So maybe the paradox isn't a reason for existential dread, but a reason for existential gratitude. Now let's talk about some of the more technical objections to the Boltzmann brain scenario, because I know some of you are probably thinking, this all sounds very speculative. And you're right, it is. But there are some solid physical arguments against it. For one thing, as I mentioned earlier, our universe appears to have a finite future. If the expansion continues to accelerate, then eventually the universe will become so stretched out that no new structures can form. This is called the de Sitter vacuum state, and it's a stable, high-entropy state where quantum fluctuations are suppressed. In this scenario, Boltzmann brains can't form because the universe doesn't have the energy or the time to produce them. The timescale for their formation is longer than the lifespan of the universe itself. So if this is the true fate of our universe, then we're safe from the Boltzmann brain catastrophe. Another objection comes from the theory of quantum decoherence. In quantum mechanics, when a system interacts with its environment, it loses its quantum coherence. That is, it stops behaving quantum mechanically and starts behaving classically. For a Boltzmann brain to have a coherent thought, it would need to be isolated from its environment. Otherwise, quantum effects would disrupt its functioning. But a brain that forms randomly in the vacuum wouldn't be isolated. It would be constantly bombarded by other quantum fluctuations. This might prevent it from ever achieving the stable, coherent state needed for consciousness. Of course, this depends on how you define consciousness and how you think it relates to quantum mechanics, which is still a very open question. There's also the objection from cosmological observations. As I mentioned earlier, the observed universe is extremely consistent. The cosmic microwave background radiation is uniform to 1 part in 100,000. The distribution of galaxies follows patterns predicted by our models of dark matter and dark energy. The fundamental constants appear to be the same everywhere we look. If we were Boltzmann brains, we would expect our observations to be much more chaotic, much less consistent. The fact that we can do science at all, that we can discover laws that work everywhere and everyone, suggests that we're not just random hallucinations. A randomly formed brain might hallucinate a universe, but it would be extraordinarily unlikely for that hallucination to be so mathematically precise and consistent. Furthermore, there's the issue of what we call the reference class problem. When we ask, what is the probability that I am a Boltzmann brain? We have to define who I am. Am I a specific arrangement of atoms? Am I a consciousness? Am I an observer? Different choices lead to different probabilities. Some philosophers argue that the question is ill-posed because we can't properly define the reference class. Others argue that we should use self-indication reasoning. We should assume we're typical members of the class of observers, not special ones. But this is a very subtle and contentious area of philosophy, and there's no consensus. Let's also consider the possibility that Boltzmann brains do exist, but they exist in a different kind of reality. Some theoretical physicists have suggested that our universe might have more dimensions than the three spatial dimensions and one-time dimension that we're familiar with. Maybe in these higher dimensions, Boltzmann brains can form more easily. Or maybe they form in other universes with different laws of physics, and we're just not aware of them. This is pure speculation, of course, but it's the kind of speculation that becomes possible when you start thinking about these problems. It opens up a whole landscape of theoretical possibilities. I also want to address the question of falsifiability, which is a key concept in science. A scientific theory needs to be testable. It needs to make predictions that could potentially be proven wrong. The Boltzmann brain scenario in its purest form is not really falsifiable. If you're a Boltzmann brain, then any test you do to try to prove you're not one could be part of the hallucination. So in that sense, it's not a scientific hypothesis. It's a philosophical thought experiment. This is why most physicists treat it as a problem to be avoided, rather than a serious possibility. A good scientific theory shouldn't lead to Boltzmann brains dominating the observer population, because that would make the theory effectively unfalsifiable. Now, let's talk about some of the positive insights that have come out of thinking about Boltzmann brains. For one thing, it's made physicists much more careful about how they think about probability in cosmology. It's forced them to confront the measure problem and to develop new mathematical tools for dealing with infinite universes. It's also highlighted the importance of understanding consciousness in physical terms. If we want to say that Boltzmann brains are impossible or unlikely, we need to understand what makes consciousness possible in the first place. This has spurred research at the intersection of physics, neuroscience, and philosophy, as scientists try to develop a theory of consciousness that could be applied to cosmological questions. Additionally, the Boltzmann Brain Paradox has implications for the arrow of time. The fact that we remember the past but not the future is a deep mystery. Some physicists have suggested that the low-entropy initial state of our universe is what gives time its direction. The Boltzmann brain scenario, with its random fluctuations, would produce observers that experience time in all sorts of weird ways. Maybe backward, maybe scattered, maybe not at all. The fact that we experience a consistent arrow of time suggests that we're not Boltzmann brains. This is another reason why the paradox is useful. It helps us think about what a universe with real observers should look like. I also want to mention that there are variations on the Boltzmann brain theme. Some people have talked about Boltzmann babies, entire infants that pop into existence. Others have talked about Boltzmann worlds, entire planets or solar systems that form randomly. The general principle is the same. In infinite time, every possible configuration of matter will form, and simpler configurations will form more often than complex ones. So you could have Boltzmann computers, Boltzmann books, Boltzmann anything. The brain is just the most unsettling example because it involves consciousness. Now, let's talk about how this connects to other areas of science. In biology, we talk about evolution by natural selection, which is a process that creates complex, ordered structures through a combination of random variation and non-random selection. The Boltzmann brain is like evolution without the selection, just pure randomness. It's the null hypothesis against which we can compare real evolutionary processes. It shows us why evolution is so powerful. It can produce complex observers much more efficiently than random chance can. In a sense, the existence of life on Earth is proof that we're not in a pure Boltzmann scenario, because life uses the laws of physics and natural selection to generate complexity in a way that's much more efficient than random fluctuation. In information theory, we talk about the probability of generating complex information through random processes. The Boltzmann brain is the ultimate example of random information generation. It suggests that if you wait long enough, you can generate any information, any story, any memory, just by chance. This has implications for how we think about the origin of information in the universe. Did the information that makes up our genes, our brains, our culture, arise through random processes, or does it require some kind of pre-existing structure or law? The Boltzmann brain scenario suggests that randomness can do it, but at an enormous cost in time and probability. In thermodynamics, the paradox highlights the importance of the second law. The only reason Boltzmann brains are supposed to form is that the second law says entropy usually increases, which means there must be rare fluctuations that decrease it. But if the second law is truly fundamental and inviolable, then maybe these fluctuations can't produce complex observers. Maybe there's a deeper principle that prevents the second law from being violated in ways that would produce consciousness. This is still an open question. I also want to touch on the cultural impact of the Boltzmann brain concept. Since it was formalized by Albrecht and Sorbo in 2002, it's become a kind of cultural touchstone for existential speculation. It appears in science fiction, in popular science articles, in philosophy forums. It's become a shorthand for the idea that reality might not be what it seems. And I think part of its appeal is that it combines rigorous science with deep philosophy in a way that's accessible. You don't need to understand the math to grasp the basic idea. In infinite time, randomness can create anything, including fake memories. This makes it a perfect gateway drug for thinking about the big questions. But it's also important to keep it in perspective. While the paradox is fascinating, it's not something that should keep you up at night. The probability that you're a Boltzmann brain, according to our best current theories, is essentially zero. The universe appears to be finite in age, finite in the amount of energy available for fluctuations, and structured in a way that favors real observers over random ones. So you can trust your senses. You can trust your memories. You can trust that the people around you are real and that your experiences have meaning. The paradox is a tool for thought, not a description of reality. That being said, I think there's value in occasionally entertaining these skeptical hypotheses, even if we ultimately reject them. It keeps us humble. It reminds us that our knowledge is provisional, that our assumptions can be challenged, that there might be more to reality than we currently understand. It's healthy to have your worldview shaken up now and then, as long as you don't let the shaking destroy your ability to live a meaningful life. The trick is to hold these ideas lightly, to use them as lenses for seeing the world in new ways, rather than as dogmas that replace your existing understanding. So where does this leave us? What should we take away from the Boltzmann brain paradox? I think there are several key lessons. First, the universe is stranger than we can imagine, and our intuitions about probability and reality break down at cosmic scales. Second, our existence is incredibly precious and unlikely, whether we're real or statistical accidents. Third, science and philosophy are deeply intertwined when it comes to the biggest questions. Fourth, our current cosmological theories must avoid the Boltzmann brain problem to be considered viable. And fifth, it's okay to entertain unsettling ideas without letting them unsettle you completely. I also want to emphasize that the Boltzmann brain paradox is a work in progress. Physicists are still debating it, still refining it, still looking for the definitive solution. It's not a settled question. New discoveries in quantum gravity, in cosmology, in the theory of consciousness could completely change how we think about it. So keep an eye on the scientific literature because this is an active area of research. Who knows? Maybe the solution to the paradox will come from a completely unexpected direction. Maybe from computer science or information theory or neuroscience. Now I want to give you a little thought experiment to play with on your own time, something that might help you internalize the weirdness of all this. Imagine you're a Boltzmann brain that just formed right now at this instant. You have fake memories of everything that led up to this moment, your childhood, your education, your discovery of this channel, everything. Now ask yourself, what would you do differently? If you knew with absolute certainty that you were a Boltzmann brain that would disappear in the next instant, how would you spend that instant? Would you panic? Would you try to do something meaningful? Would you just observe? This is a bit of a twist on the old philosophical question of what you would do if you knew you were going to die tomorrow, but it's even more immediate. It's not about dying tomorrow. It's about ceasing to exist right now, with no future, no past, just this moment. What would that moment be worth to you? This thought experiment, as unsettling as it is, can actually be liberating. It can help you appreciate the present moment, the sheer fact of being able to experience anything at all. It can strip away the noise and the distractions and leave you with the raw, immediate fact of consciousness. And that, I think, is valuable whether you're a Boltzmann brain or not. It's a reminder to be present, to appreciate the mystery of existence, to find wonder in the everyday. I also want to talk about the role of the observer in quantum mechanics, because this is relevant to the Boltzmann brain discussion. In some interpretations of quantum mechanics, the act of observation is what collapses the quantum wave function and creates reality. Now, if you're a Boltzmann brain, what does that mean? Does your observation create a fake reality? Or does it not work because you don't have a real environment to observe? This is a deep question about the relationship between consciousness and physical reality, and it's one that physicists are still trying to understand. Some have suggested that the very concept of an observer in quantum mechanics might require a real physical context, not just a disembodied brain. If that's true, then Boltzmann brains couldn't actually collapse the wave function, which would mean they couldn't really observe anything in the quantum sense. This would be another argument against the paradox. But let's bring this back to something more concrete. Let's talk about the actual calculations that physicists do when they're working on this problem. The standard approach is to use something called the path integral formulation of quantum mechanics, which sums over all possible histories of a system. When you apply this to the entire universe, you're supposed to sum over all possible universes. The problem is that this sum is dominated by universes that are high entropy, chaotic, and full of Boltzmann brains. The low-entropy, ordered universes like ours are exponentially suppressed. This is the technical version of the problem. The solution, if there is one, must involve finding a way to make the path integral favor real universes over random fluctuations. This might involve new physics, new boundary conditions, or a new way of doing the sum. It's a major unsolved problem in theoretical physics. Another approach involves something called the holographic principle, which suggests that the information in a volume of space is encoded on its boundary. Some physicists have suggested that this principle might place a limit on the complexity of fluctuations that can occur in a given region of space. If that's true, then Boltzmann brains might be impossible because they would require more information than the region can contain. This is still highly speculative, but it's an example of how new theoretical frameworks might solve the problem. I also want to mention that the Boltzmann brain paradox has connections to the so-called measure problem in eternal inflation. Eternal inflation is a theory that suggests our universe is just one of infinitely many that are constantly being created by an inflating multiverse. In this scenario, you have to count the number of observers in each universe to calculate probabilities. But different ways of counting give different results, and some ways lead to a Boltzmann brain catastrophe. This is one of the major challenges for eternal inflation theory. If the theory can't be formulated in a way that avoids Boltzmann brains dominating the observer count, then the theory might have to be abandoned or seriously modified. Now let's talk about the philosophical implications in more depth. The Boltzmann brain paradox is a modern version of an ancient philosophical problem, the problem of skepticism. How can we know anything for certain? How do we know the external world is real? How do we know other minds exist? These are questions that philosophers like Descartes, Hume, and Kant grappled with centuries ago. The Boltzmann brain scenario adds a new, scientific flavor to these old questions. It provides a physical mechanism by which we could be deceived about reality. But ultimately, it faces the same problems as older skeptical scenarios. It might be logically possible, but it's not epistemically useful. It doesn't give us a way to distinguish between being a Boltzmann brain and being a real observer, so it doesn't actually help us navigate the world or gain knowledge. In philosophy, this is sometimes called the bankruptcy of pure skepticism. The idea that while we can always imagine we're being deceived, we can't actually live our lives as if we are. We have to assume that our senses are generally reliable, that our memories are generally accurate, and that the world is generally real, because that's the only way we can function. This is where science and philosophy meet. Science gives us reasons to think that our assumption of reality is not just pragmatically useful, but actually correct. The consistency of our observations, the success of our predictions, the fruitfulness of our theories, all of these provide evidence that we're on the right track. So while the Boltzmann Brain Paradox is a fun and useful thought experiment, it doesn't actually threaten our knowledge of the world. It just reminds us to be humble about that knowledge. I also want to talk about the cultural and artistic responses to the Boltzmann brain idea. It's appeared in science fiction novels, in movies, in video games, and music. It's become a kind of shorthand for existential doubt, for the feeling that reality might be a dream or a simulation. I think this speaks to something deep in the human psyche. We have a natural tendency to question reality, to wonder if there's something more or less than what we see. The Boltzmann brain paradox gives scientific legitimacy to this intuition, even if it's ultimately resolved in favor of reality. It's a way for us to explore these deep fears and curiosities in a structured, rational way. For instance, there are novels where characters discover their Boltzmann brains, or where the entire universe is revealed to be a statistical fluctuation. These stories often explore themes of identity, memory, and the search for meaning in a seemingly meaningless universe. They ask questions like, if your memories are fake, does that make your experiences any less real? If you're going to disappear in an instant, does anything you do matter? These are profound questions, and the Boltzmann brain scenario provides a concrete way to explore them. In video games, the concept has been used to create mind-bending plots where the player character's reality is constantly shifting, and they're never sure what's real. This creates a sense of existential vertigo that can be both terrifying and exhilarating. It forces the player to question not just the game world, but their own assumptions about what a game is and what it means to play. In visual art, artists have tried to capture the image of a brain floating in the void, experiencing a fake reality. These images are often surreal and haunting, capturing the isolation and fragility of the Boltzmann brain. They remind us that consciousness is a delicate thing, that our sense of self is dependent on a particular arrangement of matter and energy that could, in principle, be disrupted at any moment. Now, I want to return to the science and talk about some of the more recent developments in this area. In the last few years, there's been a lot of discussion about whether the accelerating expansion of the universe might actually prevent Boltzmann brains from forming. The idea is that as space expands, it creates a cosmological horizon, similar to a black hole horizon, beyond which we can't see. This horizon has a temperature, called the de Sitter temperature, and it turns out that this temperature might be too low to support the kind of fluctuations needed to create a brain. There's also the idea that the expansion creates a kind of cosmic censorship, preventing information from ever being lost or created in ways that would violate the laws of physics. If these ideas are correct, then the Boltzmann brain paradox might be a non-issue for our particular universe. There's also been work on something called the Gibbons-Hawking effect, which is related to the temperature of de Sitter space. This effect suggests that the universe has a kind of built-in thermodynamic stability that prevents large fluctuations. If that's true, then Boltzmann brains would be suppressed not just by probability, but by the fundamental thermodynamics of space itself. This is still a topic of active research, and it's not settled, but it's a promising avenue for solving the problem. Another recent development is the application of computational complexity theory to cosmology. Some researchers have suggested that the probability of a fluctuation should be weighted not just by its entropy, but by the computational complexity required to describe it. A brain, even though it has relatively low entropy, has very high computational complexity because it contains a lot of information. So maybe the probability of forming a brain is actually much lower than the simple entropy calculation suggests. This is a very new and speculative idea, but it's an example of how bringing in ideas from computer science might help resolve an old problem. I also want to mention the role of string theory and other theories of quantum gravity in this discussion. Some versions of string theory predict that there are a vast number of possible universes, each with different physical laws. This is sometimes called the landscape of string theory. In this landscape, you might think that Boltzmann brains would be everywhere. But string theory also imposes constraints on what kinds of universes are actually possible. It might turn out that the only stable universes are ones where Boltzmann brains can't form, or where real observers are much more common. If that's the case, then the fact that we exist as real observers tells us something about the structure of the string theory landscape. This is a very speculative area, but it's one of the ways that the Boltzmann Brain Paradox might connect to fundamental physics. Now, I want to take a moment to address the emotional and spiritual dimensions of this paradox, because I think it's important to acknowledge that these ideas can touch on deep, personal beliefs. Some people find the idea of being a Boltzmann brain to be existentially threatening, because it seems to undermine the meaning and purpose of life. If it's all just a random fluctuation, then what's the point? But I want to suggest that meaning isn't something that the universe gives us, it's something we create. Whether you're a real person or a Boltzmann brain, you can still find meaning in your experiences, in your relationships, in your curiosity, in your creativity. The source of your consciousness doesn't determine the value of your consciousness. You are still you, still experiencing, still wondering, and that has value in itself. I also think it's worth noting that many spiritual traditions have grappled with similar ideas long before modern physics came along. Buddhist concepts of impermanence and illusion, Hindu ideas about the nature of reality and consciousness, even some mystical Christian traditions about the relationship between the self and the divine. All of these touch on themes that resonate with the Boltzmann brain paradox. The idea that our perception of reality might be an illusion, that the self might not be as solid as it seems, that everything is transient and contingent, these are ancient insights. Modern physics is just giving them a new language, a new context, a new set of metaphors. Now let me bring this back to a more practical level. How should you, as a person living your life, think about the Boltzmann brain paradox? I think the best approach is to treat it as a kind of mental exercise, a way to stretch your conceptual muscles, but not as a guide to daily living. Use it to appreciate the mystery of existence, but don't let it paralyze you. Use it to question your assumptions, but don't let it make you doubt everything. Use it to find wonder in the ordinary, but don't let it make the ordinary seem meaningless. The paradox is a tool for thinking, not a hammer to smash your worldview with. I also want to encourage you to explore these ideas further on your own. Read about Boltzmann's life and work. Read about modern cosmology and the multiverse. Read about the philosophy of mind and the nature of consciousness. The more you learn, the more you'll see how all these ideas connect, and the richer your understanding will be. And hey, if you find a solution to the Boltzmann brain problem that nobody's thought of before, you might just become famous in certain academic circles. At the very least, you'll have some great conversation starters at parties, though you might find that people start avoiding you if you bring it up too often. I also think it's fun to think about the Boltzmann brain paradox in the context of science fiction, scenarios that you might be familiar with. For example, in The Matrix, the protagonists discover that their reality is a computer simulation. The Boltzmann brain scenario is like the natural, non-technological version of that. Instead of being plugged into a machine, you're a statistical accident. Or consider the movie Inception, where characters live in nested layers of dreams. The Boltzmann brain is like the deepest possible layer, a dream with no dreamer, a hallucination with no reality behind it. Or think about the TV show Westworld, where artificial beings become conscious. The Boltzmann brain is like the most minimal possible conscious being, just enough brain tissue to experience, nothing more. These stories resonate with us because they tap into the same deep questions about reality and identity that the Boltzmann Brain Paradox does. Now, I want to talk about the future of this research, because this is an area where things are still evolving. As we develop better theories of quantum gravity, as we learn more about the early universe, as we perhaps detect signs of other universes or other dimensions, our understanding of the Boltzmann brain paradox will change. It's possible that future discoveries will make the paradox obsolete, that we'll find out that the universe doesn't work the way we think it does. Or it's possible that we'll discover that the paradox is real, that Boltzmann brains really do dominate the observer population, which would force us to completely rethink our place in the cosmos. Either way, the journey of discovery is ongoing, and that's exciting. One area of future research is the development of quantum computers. As we build more powerful quantum computers, we might be able to simulate quantum systems more accurately, which could help us understand how quantum fluctuations work on cosmological scales. We might be able to test whether certain types of fluctuations are possible or impossible. We might even be able to simulate the conditions needed for Boltzmann brains to form, at least in principle. This is still far in the future, but it's an example of how technology might help us answer these deep questions. Another area is the search for dark matter and dark energy. We know that these mysterious substances make up most of the universe, but we don't know what they are. It's possible that their properties are crucial for understanding the long-term fate of the universe and whether Boltzmann brains can form. Maybe dark energy will change over time, maybe it will decay, maybe it will lead to a different kind of universe in the far future. Any of these possibilities could affect the Boltzmann brain calculation. There's also the possibility that we'll discover new particles or new forces that change our understanding of thermodynamics at the cosmic scale. Maybe there's a particle that prevents large fluctuations, or a force that stabilizes the universe in a way that we don't currently understand. These kinds of discoveries happen all the time in physics, and they can completely change the landscape of what's possible. Now, I want to address the question of why this paradox matters for the average person, because I know some of you might be thinking, this is all very interesting, but how does it affect my daily life? And the honest answer is, it probably doesn't. You're not going to use the Boltzmann brain paradox to decide what to have for breakfast or how to do your taxes. But I would argue that it does matter in a more subtle way. It matters because it expands your mind. It challenges you to think beyond your immediate concerns, to contemplate the big picture, to see yourself as part of a grand cosmic story. This can give you perspective. It can help you deal with the small stresses and anxieties of daily life by reminding you that you're part of something much larger and more mysterious. It can inspire you to learn, to explore, to ask questions. And in that sense, it enriches your life, even if it doesn't change your practical decisions. It also matters because it's a testament to human curiosity. We don't just ask, how do I get food and shelter? We ask, why am I here? Is this real? What is the nature of existence? These questions are part of what makes us human. The Boltzmann brain paradox is a modern expression of that ancient human impulse to understand our place in the cosmos. By engaging with it, you're participating in a tradition of inquiry that goes back to the earliest philosophers and scientists. You're keeping that tradition alive. I also think it's important to share these ideas with others, to have conversations about them, to debate and discuss. That's how we collectively make sense of the world. So I encourage you to talk to your friends and family about the Boltzmann brain paradox. See what they think. See how they react. You might be surprised by the insights they have, or the perspectives they bring from their own experiences and beliefs. These conversations can be bonding experiences, even if they start with something as weird as floating brains in the void. Now, as we near the end of this deep dive, I want to bring it all together with a final thought. The Boltzmann Brain Paradox, at its core, is about the relationship between randomness and order, between probability and reality, between chance and meaning. It asks us to consider whether the most meaningful things in our lives, our consciousness, our memories, our sense of self, could be the products of pure chance. And it suggests that in an infinite universe they could be. But it also suggests that even if they are, even if you are a Boltzmann brain, that doesn't diminish their value. The experience of love, of beauty, of understanding, of wonder, these experiences have value regardless of their origin. They are valuable because they are experienced, not because of where they came from. So whether you're a real person in a real universe or a fleeting fluctuation in the void, you are still here now experiencing this moment. This moment where you're listening to my voice, where you're thinking these thoughts, where you're part of this cosmic conversation, that moment has value, it's precious, it's unique, and it's yours, so cherish it. Use it to learn, to grow, to connect, to create. Use it to ask more questions, to seek more answers, to dive deeper into the mystery of existence. Because that's what consciousness is for: exploring, understanding, appreciating the incredible fact that anything exists at all. And with that, my friend, we've reached the end of our journey through the strange and unsettling world of the Boltzmann Brain Paradox. I hope you found this exploration as fascinating as I have. I hope you're leaving with more questions than answers, because that's always the sign of a good conversation. I hope you're feeling that mixture of awe and curiosity that comes from confronting the deep mysteries of the cosmos. And most importantly, I hope you'll stick around for more videos like this, because there are so many more mind-bending ideas out there waiting to be explored. If you enjoyed this video, if it made you think, if it sparked something in you, please take a moment to like it and subscribe to the channel. Your support means the world to me, and it helps these videos reach more people who are hungry for deep, challenging, fascinating ideas. And I really do want to know where you are and when you're watching this. Drop a comment down below with your city and the time. I'm genuinely curious to map out where and when in this vast, mysterious universe our paths have crossed. Are you watching this in the bright morning light of Tokyo, in the afternoon hustle of New York, in the quiet midnight hours of London, or maybe somewhere else entirely? Let me know. Now, as I wrap up, I want to leave you with one final thought to carry with you into your day, or your night, or whatever time it is where you are. The universe is vast, mysterious, and often deeply weird. It contains phenomena that challenge our understanding and push the boundaries of what we believe is possible. But you, my friend, whether you're a Boltzmann brain or not, are part of that universe. You are the universe experiencing itself. You are the cosmos made conscious. And that is an incredible, miraculous thing. So, as you go about your day, as you live your life, as you continue your own journey of discovery, remember to look up at the stars, to wonder, to question, to appreciate the sheer improbability of your existence. And remember that no matter where you are, no matter what time it is, you are part of a grand cosmic story that we're all writing together. So wherever you are, whatever time it is there, I hope you have a wonderful day or a peaceful night or whatever comes next in your corner of reality. Thank you for spending this time with me, for letting me share these ideas with you, for being part of this amazing community of curious minds. Keep questioning, keep exploring, and keep that sense of wonder alive. I'll see you in the next video. Good night and goodbye.